Okay, so we covered the anatomy of basic model-based parallel, then we talked about doing random shooting in MPC, and then we talked about using MPPI, and we started talking about uncertainty a little bit, and then we ran out of time, right? And then today what we're going to try and do is finish up uncertainty-based models. How do we model uncertainty? How do we use it in model-based parallel? We talked about policy optimization stuff. We talked about a little bit in the paper readings, but we'll rush through it. And lastly, we'll talk about how to get this to work with images and high-dimensional observations. Okay, so to continue recapping a little bit, we have the basic anatomy of a model-based parallel algorithm. You collect a bunch of data. You train a one-step model with supervised learning, maximum likelihood, and then you do planning to find the best series of actions from a particular state, which maximize the reward under your learned policy P theta hat, right? And so you have P theta hat, you roll it out a bunch of times with some actions, so you choose the best series of actions, you execute the first step, and you repeat, right? And so the MPC is letting you deal with errors in your model or unexpected events. And you're just planning with random shooting, right? And so it's better than just doing open loop planning because of this feedback and you're continuously feedback. So that's the first version of the algorithm that we had. Then we said, okay, like this is searching for a needle in a haystack, so we're going to do better. And instead, what we're going to do is we're going to try and iterate through this loop where we say we're going to sample a bunch of actions, but rather than just choose the best amongst those, you're going to refine the action distribution by weighting it according to the reward. So you're sampling more near things that have higher reward, right? And so this algorithm is called MBPI. And so you sample a bunch of actions, roll them out to your model, weight them with reward, and then refine your action distribution to be closer to things that have higher reward, right? And so you say you're going to take an action distribution weighted by exponential sum of the rewards along that trajectory, and then refine your action distribution and sample again, right? And so there's some questions on Ed about where this actually fits in the anatomy of the algorithm, right? So the way that it's going to fit is it's going to replace, like this procedure is doing random sampling, choosing the best thing. MPPI is just going to replace this procedure, right? So you're still going to do data collection, you're still going to do model learning, but when you're doing planning, rather than just sampling random stuff and choosing the best, you're going to run this MPPI procedure, all as an internal step of planning. And so instead of just doing random shooting, choose best, you're going to do random shooting, choose best, update your action distribution, try it again, try this like 5 times. Then you get your best action that you execute in the environment, right? And so MPPI all lives inside that like planning box. And so you can think of MPPI or random shooting as just like replacements for policies. They're like implicit policies, right? They're using the model and they're trying to like find the best thing under your model. Whereas in model PRL, you learn the policy. Here you're like constructing a policy on the fly.
I was wondering if this like is related at all to something like PXPP, because I noticed it had like exponential updates to the weights, which is similar. Oh.
Yeah, it's related. It's related to like RWR, EXP3, and like natural policy gradient. Like all of them are like kind of exponentially weighting the higher reward higher. So they're all the same idea. Like anytime you put a trust region on things, you get this exponential. Okay, so that was MPPI. So you can just think of it as a repeatedly trying action sampling with reweighting by sum of rewards. And then we talked a little bit about uncertainty, and we said that, okay, we have this like compounding error that happens when your model is rolled out for repeated numbers of steps, right? So we say you're going to keep rolling out your model is going to get worse and worse over time. So you have like this compounding error because you like make a little error, this goes back into your model and make a bigger error. So you have model hallucination with horizon, right? The same way we did for imitation learning. And our fix was to say, if we can measure uncertainty, if we can measure when we've gone out of distribution, then you can penalize these hallucinated trajectories, right? So you can say, I don't want to do any, I don't want to like consider actions that are hallucinated to be good if my uncertainty is high, right? So like this may be high reward, but it has high uncertainty, so it's unlikely to be true, right? And if it's unlikely to be true, then we probably can't trust it as an action to take in the account. And so what you can do to deal with this kind of thing is to just measure uncertainty. So measure by uncertainty, I mean like how out of distribution you are, and then downweight things that are out of distribution. And what we started talking about was like techniques to measure uncertainty. Yeah. So the main point is that you will have compounding error when you like roll out models for longer and longer. If you remember the paper readings, MBPO has like really short rollouts, right? The reason is because it like starts deviating. If you want to deal with that, if you can measure uncertainty, then you can downweight those things that are hallucinating. Okay, so that's kind of where we stopped. And we discussed two different types of uncertainty. We talked about aleatoric uncertainty, which is stochasticity in the environment. Right, so if the data naturally has stochasticity, like see at this point, there's like stochasticity in the environment, that's aleatoric. Things that are like uncertain because of lack of data, like there's no data here, so you have uncertainty over which of the functions it is. That's what we call epistemic uncertainty, right? And so we really want to capture not like aleatoric uncertainty is easy to capture. You just have like a more powerful generative model than a Gaussian, right? You say you have like, you know, a diffusion model or a energy-based model or whatever, some powerful generative model. It's easier to capture aleatoric uncertainty because it's just like a multimodal distribution, right? It's saying that S and A can go to S prime or it can go to S prime prime, right? And so you can almost think of aleatoric uncertainty saying S and A can go to S prime, S prime prime, S prime prime prime. And so you just need to have like some multimodal distribution, right? But epistemic uncertainty is more, it's like more of a Bayesian idea where it's saying that if you don't have data on some S and A, then you should have some uncertainty on what S prime goes to, right? And so that's the type of uncertainty we're going to try and capture today. So like uncertainty that comes from lack of data, because that's what's going to cause your model to like the lack of data. If you go to regions where you don't have data, that's when you have hallucination. Okay, so what we're going to discuss next is how do we measure epistemic uncertainty? What are some practical ways to do it? And then how do we use this for planning? All right, okay. So the structure of our lecture today is going to be, we'll start with uncertainty-based models. We'll talk about policy optimization, data spaces. Then we talk about control as inference, the formalism, and then we start an introduction to variational inference as a tool to study control as inference. Right? And so the first year model-based and the last row unification. Okay. So what is uncertainty, right? So uncertainty in the sense that we want, which is epistemic uncertainty, is really P of theta given D, right? So which means that like, what is the likelihood of a particular model that is consistent with your data T, right? And so this is like a Bayesian concept, right? It's like in maximum likelihood, you try to like fit theta, which maximizes you know, you do something like this, right? You say, I have some data, sample from some unknown distribution P, and I try to like estimate the theta, which maximizes likelihood, right? And so you try to find a single best theta, and that best theta is like the thing that best explains the data, right? But it doesn't capture any uncertainty. There may be many models that capture the data, and it doesn't capture any notion of uncertainty. And so instead of maximum likelihood, we're going to try and get something that looks more like a Bayesian estimate, right? And our Bayesian estimate is going to be P of theta given D, which means that P of theta given D is going to be your posterior over theta consistent with your data, right? So it's going to be just by Bayes rule, P of theta given D is going to be equal to P of D given theta times P of theta by P of D, right? That's just Bayes rule. And P of D is this integral, right? P of D given theta prime times P of theta prime integrated over all P theta prime. Now, this is nice because it says you're not going to just have a point estimate of theta, you're going to have a distribution over theta, which is like essentially weighted by how likely it is to be consistent with the and the prior, right? And so, you have a question? No. And so the P of D given theta is likelihood, right? So it's basically the same thing that we had earlier. It's like supervised learning. It's like how likely is Y given X and theta, right? It's like how likely is the data to be produced by a theta? This P theta is like how likely is something under the prior. So you have some prior distribution over models. You can choose what it is. You can say simpler models are more likely, or anything like that. And then the point is that given a prior and a likelihood, so this is the same thing as maximum likelihood. this is a prior, you can estimate a posterior P of theta given T, which is a distribution over parameters, right? And so essentially, imagine it's a distribution over neural nets, if you will, right? So the distribution over parameters of your function that are consistent with the data, right? And so here's maybe one way we can illustrate it. If you look at this figure, right, you can think of these different lines as different functions, right? So each of them are different functions that are consistent with the data, right? And what you want to do is you want to say that, okay, near the data, all of them are consistent, but away from the data, you want to maintain a distribution over different functions which are consistent with the data, right? Now, if imagine that I had a function that was like this, right? That is obviously not consistent with the data. And so it's going to be low likelihood near posterior, right? And so you're going to maintain a distribution over all possible function parameterizations, which are consistent with the data. And so that's the point of like your Bayesian posterior, right? And so the point of like, when you're doing uncertainty, you want to like estimate this posterior by Bayes' rule, and this is going to give you a measure of like uncertainty. Now, why is this difficult to compute? The integral is the denominator, right? So you have this like partition function, which is like a pain in the ass, right? And you have to like integrate over all possible parameters, which is like an infinitely large space, right? So you have to integrate over all neural nets, which is crazy. Right? And so it's difficult to compute this directly. And so a lot of the techniques we'll talk about later are how to avoid this integral computation. Yeah. Yeah. So like usually in maximum likelihood, what you'll do is you'll say maximize log P of D given theta with respect to theta. You could, but you'll have a log integral then. No, well, you won't be able, like, if you want the posterior, you don't want to just find the best theta. You want to actually estimate the distribution of the theta. Like the probabilities matter. So you can take log, but you need to get the value. You can't just take the gradient. So if you take the gradient, then the constants don't matter. But if you're trying to get a likelihood, then the constants matter, right? Like, so if I want to like measure uncertainty in a calibrated way, then it matters, right? So I care not just about like, what is the best theta here? So that's a technique called map, right? So when you try to say maximize log probability of this thing with respect to theta, that's what you'll call map, right? And map is doable because as you said, like this thing doesn't depend on theta, right? But what we care about here when we're doing planning is to measure uncertainty so we can penalize it, not just the most likely. Good question. Yeah. Okay, so it's difficult because you have to compute that denominator. It's an infinite integral, so hard thing to compute. And so we're going to construct a bunch of approximations, right? And so here are two popular ones. The first is the Bayesian neural net, and the second is an ensemble. So Bayesian neural net is really simple, right? So it's going to see, do I have a slide on it? One second. Yeah, there we go. So Bayesian neural net is saying that rather than having a single weight for whatever edge in a neural net, you're going to have like a distribution of weights, right? So every weight is not going to be a single weight. You're going to have a mean and a variance for every weight. And so it's going to try and parameterize a distribution over neural nets by a product of distributions over different weights. Okay. And so Bayesian neural nets would typically try to make the assumption that all the weights are independent. And then try to like use a technique called variational inference to find an approximation to this Bayesian posterior. And so we'll go over variational inference in a lot of detail at the end of this lecture. But for now, they just treat it as a black box, right? It's just a technique that's going to use this approximation that weights are completely independent and try and estimate a distribution over neurons, right? So it's going to say distribution over the parameters theta is going to be a product of distribution over individual weights. And then we'll use this technique called variational inference to solve it. Now, the challenge with it is that it's like hard, like Bayesian neural nets don't work very well, at least not yet. And so we're going to just try something simpler, right? So Bayesian neural nets, the idea to take away is it's going to have a distribution over weights. We're going to use variational inference to solve for those, approximate that distribution over weights. Instead, we're going to try this thing called ensemble methods, which is easier, right? So all it's saying is that rather than learning One parameterization, we're going to learn k different neural nets. I think last time we talked about dropout, something similar, right? And so the point is you can learn an ensemble of models. And the way you train things is very simple, right? You're just going to say all of the models are trained on the same data. They just start with different initializations. And so where there's data, they're going to agree. Where there's not data, they're going to disagree just because of the nature of neural net optimization. And so often you can train them on all the same data, and variance of the ensemble is often a good approximation to the Bayesian posterior. And there's like some principal work from NYU that talks about like why this is true. I can send it on Ed. But the point is that it like works really, really well because all you have to do is train k neural nets. That's it. And so in model-based RL, you just train k dynamics models, right? And then you measure the difference of the variance between them as a means of like measuring certainty. Right? Okay, so does that make sense for measuring uncertainty? So there's Bayesian neural nets, they're harder to use, ensembles that are easier to use. And we just want to now use these like, so all you're going to do is to go from deterministic models to uncertainty models, just train k neural nets. You measure the variance amongst those neural nets predictions, and that'll give you a measure of uncertainty. Right? Yeah. So I guess theoretically, you would want to use different samples IID from the same data set. In practice, often just because the neural nets are initialized differently and optimization goes differently, they will be different in areas that you don't have data. It's a good question. Yeah. Okay. So the question becomes, how do we actually use these dynamics, these uncertain dynamics for dealing with this model hallucination or compounding error? So the easiest thing you can do is just take expected value under the uncertain dynamics, right? So rather than saying, I want a policy or a planner to be good under the dynamics, right? So if you remember our random shooting thing from earlier, right? We're just going to say there we just said, hey, we want to run forward through the dynamics and we want to do the actions that are good under a particular, like our best estimate of the dynamics, right? Now what we're going to do is instead of having the best estimate of the dynamics, you're going to like at every iteration, you're just going to sample, like let's say you have I of these in an ensemble, you're just going to sample one of them in the ensemble, right? And so what that results in is a robust update, which is saying that it has to be good, not just against a particular one, but against the mixture of all of them, right? And so forwarding back to our slides here is saying that you want to say that like you want to be good, not just you want to be good not just on a particular dynamics model, but if you had k different dynamics model on your ensemble, you want to be good in expectation across all of those dynamics models, right? And so since you know that in regions where you don't have data, these dynamics models will disagree, right? So if you're hallucinating things, these dynamics models are going to disagree. You're going to prefer things that are like low uncertainty because they're like predictable. And so the simplest thing to do is to just treat your ensemble of dynamics models as just like a stochastic dynamics model where you pick one of the ensembles at every time. And then you're just trying to find the series of actions that are best across the mixture of all the ensemble elements. And that's going to let you get something that's robust to this kind of hallucination because the variance across these ensemble elements is going to be high in regions where you don't have data. Yeah. Yeah, so all of this is like planning with your best estimate of the current model. And then when you go to exploration, you want to collect more data, right? And so I think this is saying like, how do I get the best plan under my current collected data? And then you have to think about the next time I go and collect data, which data should I collect, right? And so maybe those are two different processes. And Andrew's going to give an excellent lecture next week on exploration. Okay, so the point here is that you can just like do something where you have a mixture of dynamics models and you just train against a mixture of dynamics models and it does way, way, way better. And so we'll try doing that in our homework where we show that if you train on a mixture of dynamics models, it'll do better than just a single one, right? And the logic is that in areas where dynamics models don't have data, they disagree a lot. And if you disagree a lot, it's hard to get a single policy that satisfies all of them. Whereas in regions where you do have data, the dynamics ones are consistent, and so it's easier to find a policy that is optimal across all. Now, that's one way of doing it. And a way that I like a little bit better is trying to be pessimistic. Sorry, go ahead.
So earlier, we talked about like, if like one step at a time, like to like basically get back on track.
Yes.
My question is like, in this case, like, why don't we have some sort of heuristic where it's like, if we're in a really uncertain area, why don't we just do that, stop and then calibrate ourselves?
Yeah, there are methods that do that, that try to like plan how to get back to uncertain regions, and some of them are from our group. But I think that's like more active research that establish it. But yeah, it's totally good idea. And people do that. Like there's a nice paper called Data as a Demonstrator, which tries to like establish a density of establish high density regions and plan to get back to the high density regions. The challenge is that if you don't have data in the low density regions, like how do you know how to get back? Right, and so that's the trick. The other thing you want to remember is that all of this is in imagination. Like all of this planning, this is not like, it's not like I acted in the world and I came to this region and I need to get back. It's all in imagination. And so what I can do is just discard things that are like high uncertainty in imagination, rather than if I was executing in the world and I got here, then I want to think about how to get back to the data, right? And then it's tricky to figure out how to do it without complete data coverage. That's like an interesting research. But yeah, we're working on things like that, so you should come talk to me about it. It'll be fun. Okay. And so the second thing that we can do is we can say like just be pessimistic, right? The earlier thing we were saying is try to maximize the expected reward under the uncertain ensemble of dynamics models. The other thing you can do is you can say that anywhere where the model uncertainty is high enough, you just like penalize the reward, right? And so we can say that rather than just hoping that it's really hard to get a policy that is good across diverse dynamics models, you can explicitly say, I'm going to take the reward and I'm just going to add a big penalty based on the variance between the model predictions, right? And so it's going to say that any action that takes me into a highly uncertain region, I don't know what to do. And so I'm just going to keep this. And so we're going to talk about this in a lot more detail offline reinforcement learning, but the idea here is really just be pessimistic in places where you don't have data. And so it's like, I don't know what to do beyond my data. Let me just stay within my data. So anything that is like going beyond your existing data, so I don't trust it, penalize it. And so you can only take actions that are good in your region of confidence. Why might that be bad? Like, when might that be bad? You're just being pessimistic. Never go beyond what you see. You're gonna trapped in local minima. Yeah, that's exactly the problem of exploration, right? So like often the tension here is that you're trying to be pessimistic to avoid over exploiting your model, but you're trying to be optimistic to collect more data, right? When you're on an online setting. And so that's kind of a trade-off that you have to handle. Okay, does this make sense? So the point is we establish uncertain dynamics by training an ensemble, and then we incorporated that uncertain dynamics into planning by just saying either we maximize expected reward over the whole ensemble in expectation, or we penalize things that are like high uncertainty by being pessimistic. How do you just like we predict from k different ensembles? You look at the variance between elements, right? Like
That's the acid.
Yeah, from your ensemble, right? So you predict k different S primes, and then you like measure the variance of the different S primes. You take the mean and the variance. Or the I don't know. We should try it. But yeah, I don't know the answer. I mean, I guess that would make sense, although it's not a consistent objective, so it's not clear that it's doing, but yeah, I don't know. You should try it and tell us what happens. Okay.
So the way it's looking now is that like if like for example we're just penalizing by variance, and does this mean that like let's say there's a section of work like prediction, where the models all agree. Like there's very low variance, but it's also like a bad trajectory. So like in this case, that one we penalize.
But the reward is for the.
Oh yeah.
Okay, so this is like kind of the logic behind lots of literature on offline reinforcement learning and being pessimistic. But yeah, it's as simple as just like this is how the homework will build up to, but we're just gonna say train a single dynamics model, do MPC, do MPPI. Now you want to do MPPI in one model, do MPPI in 8 different models. That's it, and tends to work a lot better. These are some examples of this. Basically, this algorithm is just MPPI on ensembles of dynamics models, working in the real world, working on tasks in simulation, which are fairly complicated, high dimensional. And so they do pretty short horizon look ahead rollouts. Like if you look at this, that D, that big D is not very large. Still like 10 to 15 steps. But it does work pretty well on these sort of problems, right? And so the magic sauce with model-based RL often is you want to do short rollouts and you want to have like really dense rewards. So that if you, when I say dense rewards, I mean like very informative rewards. So that even short horizon rollouts give you, an action in the right direction. And so that's like the dirty laundry in lots of model-based RL. So model-based RL is hard when you have really long horizon planning and you get it's like if you have to navigate a maze and you only get reward at the end, long model-based RL is going to struggle with that because it's going to like hallucinate crazy stuff. It goes through the walls. But if I have like a good reward which gives me like path distance and you do like 10-step look ahead, model-based RL works good. So that's they're not going to write that in the papers, but that's usually what happens. Okay, so that is how we kind of incorporate uncertainty into this whole thing. And next we want to think about policy optimization. Any questions before we move on? Yeah. Yeah. I think some of the work from Mohawk and others try to do like blending models that do different. Mohawk is one of the PhD students in Byron's group, but he does cool work on blending different levels of look ahead. And because it's kind of the same as GAE, if you remember from policy grids, it's like models might be biased, but low variance, and few functions might be unbiased, but high variance, right? And so often you like trade off how many steps look ahead you do versus like slapping on a terminal value function and you like you blend together different levels of look ahead. So look at some of Mohawk's work, it's really important. Okay, cool. So let's keep moving. Yeah. Oh, yeah. So basically in MPPI, the first version of MPPI we talked about, you do MPPI through one dynamics model, right? So you just run it forward to one dynamics model and you repeat the process, right? All we're going to do to incorporate uncertainty into it, you're going to learn an ensemble of dynamics models, right? You're going to learn K of them, and then you're going to do MPPI the same way through the ensemble of dynamics models. So you're essentially going to pretend that your dynamics was a mixture of dynamics, right? Where the mixture is across different ensemble elements. So almost think of it as like you're doing MPPI now, but your dynamics model is not one of the dynamics models. It's like every time you want to sample, you sample one of the elements and take a step forward. Right? So you're sampling on the mixture, and then the mixture is going to incorporate uncertainty. Okay, cool. Great. So that's how we do uncertainty. And there's still issues in this, right? So we want to apply this to robots. We want to apply this to robots operating at high speed, right? And so some of you brought this up. But if you're operating at high speed and every single time step, you have to run this expensive MPPI loop, it's like kind of a pain with any decently sized model, right? And so one of the issues here is that it's extremely hard to run in real time. In the sense like I have to run like K step look ahead. K is like 100 and my model is a huge neural net model and I'm running on an edge device like a small robot dog or something, then it becomes like pretty expensive to do that meaningfully. And so it becomes hard to run in real time, right? And so the next idea that we're going to explore is like, how do we take the benefits of models and amortize them into something that can run in real time, right? And so we want something that can run on an edge device like a robot, but run in real time. And we're just going to do amortization, which means we're going to take a model and we're going to use the model to learn a policy. And a policy at test time doesn't have to do any like internal planning. It just needs to run your policy. Right? So it's going to say, you're going to have a, just like we did in like model 3.0, you're just going to take in S, you're going to output A, just do one forward pass of your neural net. You don't need to like go through the planning process. But the key is we're going to use a model in order to train our policy, right? And the benefit here, this is the same thing we talked about in paper readings with MBPO. Like the point is, I think the point that I find compelling is it like amortizes planning so that you're still using the model to train your policy. So you're getting data efficiency benefits, but it's running fast enough for real time. And so the idea is super simple. What you're going to do is you're just going to say, my model is going to generate a bunch of data for policy optimization. Right, so model is going to, you can think of your model as a generative model. You can stick in an S and A, get an S prime. Now you have S, A, S prime, R tuples. You stick it into any policy optimization framework, SAC, actor critic, policy critic, whatever you want. And then you get a policy that you can run in real time, right? But you're planning and hallucination. And so you're planning by like hallucinating trajectories from your dynamics model, right? And so the whole point here is that the hallucination is going to give you data efficiency, but your planning is going to give you real-time execution. You can like run things through. Now what's the issue here? Like why is this not just trivially pretend that your model was the simulator and just like run actor critic? Would that work? Any thoughts? So all we're going to do is we're going to just say, learn a model, pretend the model is your simulator, just redo all of your policy grid and actor critic equations, but just sample from your model instead of the true environment. That's it. Same issue with uncertainty. That's right. You're just going to have like compounding error blow up, right? But kind of forward. Yeah. So the issue here is that long horizon rollouts can deviate. So if you're trying to generate lots of data, if you just pretend it's your simulator, you're just going to get blow up. And so that's why algorithms like MBPO, which we covered in lecture last time, are going to do short horizon rollouts starting from real trajectories, right? And so you're just going to like, William remembers, but if you like start from points on your data and do little rollouts from there, it's kind of like where your data has support. And there's a trade-off between like the length of horizon and like or the length of your rollout and compounding error, right? So the longer your rollouts, the more data efficiency you'll get, but at some point the data becomes meaningless. And so you do like 1 to 25 step rollouts, no more than that. And often in practice, you like start with smaller rollouts, and then as you get more data, you anneal them out to like longer rollouts. But it's never super long in any of these methods, right? And so this class of methods started from Dyna, which is in the 90s, but it's basically like Dyna tries to do like simpler models. They weren't big neural net models, but they try to do data generation, and MBPO tried to build on that and do short horizon rollouts with large neural net models, right? That's basically it. And so the training procedure, do you have questions on it? No, okay. The training procedure here is that we're gonna learn a bunch of models. You're going to use those models to sample fake data, resetting things in the training data and running little rollouts from. You're going to do policy optimization. Often you run like actor critic methods on that hallucinated data. You roll it out in the environment, collect more data, right? You get the policy, you can roll it out in the environment in real time. And then you collect more, you train your models more and you repeat, right? So you learn models, generate data, train, roll out an environment, repeat, right? So the trade-off here is that this step is now way more expensive because I'm like running neural net training in there. Whereas in all the previous things, MPPI, etc., it's like you don't have to do any neural net training beyond learning the model. You're doing all of that at test time, right? And so this is shifting the burden of computation to training time, but it allows you to run in real time. And so that's great for things like robots, because at test time now, all you do is you like The world gives you an observation, the policy gives you an action, you just repeat, right? No need to do plan. So that's basically the whole point of like these types of methods that like try to generate data from learned models. It's really useful for robotics because you want to run things in real time, you want to run things fast, and you want to run things on like relatively cheap hardware, right? And so, yeah, if you're ever doing model-based RL on with a large model, try to amortize it to a policy.
So in that, then there's no more like real world exploration, like the possible current size.
So there is real world exploration, but the real world exploration happens right here. So you're gonna have like, we'll have the models learn. You're gonna generate data with this branching thing. You're gonna do policy optimization, and then you're gonna roll out in the environment with a bit of noise added to the policies. And so that's where the exploration is gonna happen, right? But in your policy learning, you're not gonna do exploration. Right? So your policy learning is like, your exploration is gonna be used to like collect data, which will update your models better. But in here, you're just going to use whatever data you hallucinated. And usually what you do is you mix together real data and hallucinated data and train on a mix. Question. Okay, so the general procedure looks something like this. Gonna start with data collection, do model learning, one-step models or ensembles of one-step models. You're going to then collect some data in the environment by resetting the states along the trajectories that you actually collected in the real world, do little branching rollouts from them. You're then going to do policy optimization, right? And then you're going to collect more data with slight noise on your policies and then repeat the whole process, right? And eventually your like the whole point is that your policies should get better a lot more quickly because your models are going to be able to generate some sensible data, right? And so the bet that you're making is that the model generated data is not all garbage. It should be giving you some generalization beyond your just real data. So you can think of after predict as just doing data collection, policy optimization, data collection, policy optimization. Here we're just adding these two extra steps, and it gives you data efficiency if this data is not all garbage. Yeah. I think there's multiple reasons. One of them, like the reason I think it makes sense over MPPI style methods is because planning at that sentence. But over SAC type methods, you do it because it's generating more data. Yeah. Okay. So again, this is one of my grad school colleagues. He had a paper where they actually do this kind of policy amortization with PPO or TRPO at the time. And they were able to get it to learn pretty quickly. This was back in the days when the PRP was still functional, but it's basically the algorithm I told you about. Is not doing accurate predict, it's just doing policy gradient, but it's the same type of method and learns in like 10 to 15 minutes of training. And it's able to run in real time. So you see that it's like not jerky, it's like operating with torque control in real time, right? Because it's running a policy. And so it's going to collect a bunch of data, use that data to train a model and train a policy, and then use the policy to execute in the real world, update the model, update the policy, repeat, right? So that's the basic paradigm.
Like that.
Mm-hmm. Usually they use like in that task, they use the distance of the end effector from the target. So like the target is when the like block is properly stacked. So they cheated a little bit in that they like didn't want to deal with the perception here. So let me just pause this. So they didn't want to deal with perception here. So they didn't want to track the blocking stuff. So the reward is basically the distance from the end effector to the target end effector where the block is like Legoed, like attached. And so it like only gets that reward when it actually like plants the arm in the right place. And so it's like purely a proprioceptive reward, only relying on like where the arm is. But it has to reason about the dynamics of the environment. It has to reason about the collisions with the block. But yeah, there's often a trick that we use at Berkeley a lot, which is like we do tasks that are really just like teaching, but are like with dynamics in there. So you don't have to deal with reward functions in the mix. Like if you had a block which you have to pick in place, that's like a lot harder. Yeah. No, that's what I'm saying. There's no perception. I'm pretty sure. Yeah, I'm pretty sure this is no percent. So it doesn't matter.
So this might be naive a little bit, but if I change the like environment, like the font
Yeah.
structure, you have to relearn like the model.
So if you had done it from perception, then you would maybe not have to if you train across enough diverse scenarios because it might generalize. Here it's blind, and so from the perspective of the blind robot, the world has changed, and so the model is no longer blind. Yeah, that's a great question. Cool. All right. So that was policy optimization with models, and the last thing we're going to cover in model-based RL is how do we get these things to work with images, right? So far we've just talked about blind policy or blind models. We want to get this to work with like high dimensional things like images, right? And so, the challenge here is how do we go from little Mojoko environments or the fetch environments, which are low dimensional, to things like waypoint navigation or VM control, or just like robots that are operating from first-person sensory, like cameras or RGB or that, right? And so you want to deal with significantly higher dimensional image-based domains. And so why is this difficult, right? It's difficult because generating states in a model is kind of like generating videos when you're going from high dimensional spaces, right? It's just controllable video generation. So it's saying video generation if you fed in actions into the model, right? So video generation is usually uncontrollable, but in dynamics modeling, you're trying to generate future frames, which are future videos when you just take in actions, right? And so what makes that difficult? You can see here that this is from the bear data set where they just like are just pushing around objects in a bin. But you can see like how blurry it gets, right? Just within like 10 to 15 time steps. And like for many different data sets, you can see that like things tend to like hallucinate like weird stuff, right? You can see that it's like going through objects, it's getting blurry. If this was a couple of years ago, it's better now, but it's still a hard problem, right? Or you're trying to synthesize human motion, it like quickly gets blurry. And the difficulty often is that predicting over like all of the issues of compounding error just get worse in image space, right? If you have an image, you're generating an image and sticking back into your model, like it's gonna blow up. Right? But the image space is larger, it's harder to generate. The errors, it's a harder problem to drop the errors down. And so the errors tend to blow up. Plus, often videos are multimodal, which means that you take the same action and like you'll have different things happen. The other issue that often happens in robotics is that they're partially observable, which means that you don't know the full state of the world. And so you don't have full state of the world, so you can't actually predict exactly what's going to happen. If you just took in the current state of action, you don't know what's going to happen next. And so a lot of the challenges are related to long horizon prediction, partial observability, and stochasticity, right? And like a lot of the recent work, Sora and latent diffusion, try to fix some of these problems. But today we're going to talk about a particular class of models called these streamer models. They're quite effective. But the key idea here is that in normal model-based RL, you learn how to go from S and A, that's prime, right? You learn a dynamic model to go from like positions of the arm and the objects, actions to the next positions of the arm. You don't have that from images. So instead, you're going to construct like what you have here. You can see it's a little hard to see, but like the S's and A's are all observed. It's like a little bit of it. But the point is that you can observe the states. But in most image-based settings, there's like a state of the world, which is unobservable. And you can only observe observations, which is your camera images, right? And so it's like not an MDP like we've been talking about, it's a BOM-DP, that it's partially observed. And so these class of methods are trying to deal with these BOM-DPs by learning latent state space models. So rather than learning dynamics from state and action to next state, they're going to learn from observation to state, state to next state back to observation, right? And so maybe this is more clear. Do I have a figure here? Okay, doesn't look like I have a figure here, but maybe I can draw it here, right? Which is you're going to go from observation to state, right? Or you can even call this like a latent, right? You're going to go from latent and action to next latent. And you're going to like reconstruct from the next latent to the next observation, right? And so like these are what you call these recurrent state space models, but basically they have the structure of there's like a recurrent model that is like representing latent dynamics. So A1 goes here, A2 goes here. Sorry, this is not ideal. Maybe, yeah. So the way that it works is that you have this partially observed process and you try to learn a recurrent state space model. So it goes from observations to like a latent and action to like the next latent. And you can have like a recurrent model in like this hidden state space, right? And at each step, you try to do like reconstruction of future observations, right? And so the difference is that rather than trying to predict directly in observation space, you like go through this recurrent state space, right? The recurrent state space is like your inference on what the like states of the world are, right? And so these models typically, we're not going to go into too much detail, but they typically have a bunch of different objectives, right? They like have an encoder which tries to go from your observations or your history of observations to a latent state, right? So as I drew earlier, it's trying to go from a history of observations. So like, trying to go from a history of observations, O0, O1, O2 till OT. Tries to go into some sort of model. That model gives you your encoder. Encoder gives you some ST, often called ZT, right? That's your like latent state. So that's the first step, right? You're trying to go from your raw observation, things like images, like a latent state, which is much lower latency. And then you're going to do dynamics in your latent state, and then you're going to come back out to your high dimensional space, right? So the first thing we'll have is an encoder. The second thing you'll have is like an action condition transition model in the latent space, right? So you're going to have, you know, your history maps up to like your latent space. And then in your latent space, you're going to have like a dynamics model in there, right? And so if you remember how we did normal model-based startup, we essentially could observe this. Here we're only going to observe this. We're going to infer latent space. You're going to learn latent dynamics. So the latent dynamics predict the next latent, but this is still abstract, right? So we still need to ground it. But it's saying, take the current observation, map it into a latent. Latent and action give you next latent, right? After you have the next latent, you're going to have a decoder, which is trying to decode the next observation. Got to be a better way than redrawing this every time. But so you have HT goes up to ZT, ZT and AT go to like ZT plus 1, and then your decoder goes back to OT plus 1, right? And so you have an encoder, latent dynamics. So this is trying to say like, take your history, predict the latent space, predict the dynamics in the latent space. Dynamics in the latent space does reconstruction, right? And then lastly, you're going to have something that predicts reward, right? So you're going to have your same history goes to latent space and action go to like future latents. You're going to have one thing that tries to predict future observation, or OT plus 1, sorry, and another thing that tries to predict future reward, right? And so the whole point is that in your original state space, you knew the function that mapped from state to reward. Your latent state space is something that is just being optimized. And so you need to be able to like plan in the latent space. You need to have a reward that you can predict from latents, right? And so you're going to learn a predictor of reward from the latents. You're going to learn latent dynamics. You're going to learn reconstruction, and you're going to have something that encodes. So you can think of this as encoding, forward dynamics, then predict the next observation and predict the next reward.
Also, it's like you need the reward function. You also just plug in the observations plus 1, 2.
Yeah, so the often in these methods, the reconstructions are not perfect, but they're good enough for planning. And so the nice part about this is like, I may not be able to generate the videos perfectly, but I'm still able to choose the actions that I react, right? And so that's why it's like, if you have another, if you like, essentially what you're saying is like, predict the observation and then kind of go back through my reward function this way, right? And like, if that is not a great prediction, then it kind of breaks it. Whereas if you go from the late, you skip it.
Is there a reason why like we can't like if we have like a model that's expressive enough, just like go from like to like skip the observation part because
Oh, because it becomes ungrounded then, like as in, you could just have zero. Like everything could be zero. And so there's a bunch of methods, some from our group too, which try to like avoid this reconstruction stuff, because reconstruction has lots of problems, right? For instance, you have like uncontrollable elements, you have a noisy TV, it's gonna like totally fuck up your model. And so this is gonna have issues with it. And so people try to avoid reconstruction, but you need something to ground your model. And so what folks have done is, because otherwise it's just degenerate, right, as an objective, was like, the best thing that to predict is a constant. Right, so like a couple of methods that come to mind. One is that you just predict future reward. Right? And future reward is still a grounding signal. You can't predict nonsense if you need to predict future reward. And so that often helps. It's just like, if reward is sparse or, you know, it messes up optimization. Another thing people do is that they like do this self-prediction, but they use a previous copy of like the weights to like set up the targets. And they have these like self-prediction methods. This is often in Bacon, but that kind of works, but I don't really understand why. But I would say observation is usually the most stable, and if you want to get rid of observation, predicting future rewards and values is also a good question. But in general, the more we can get rid of reconstruction, the better. But I think we haven't figured out all the moving parts to do that. Right? And so Jan LeCun has a new set of architectures called VCHEPA and these kinds of things, which try to do that, but they're still being worked out. But they're very promising. I would look at them. Okay, so we have all of these different losses, right? And then you do a big old sum, right? So you say the losses are observation reconstruction, right? You're trying to like reconstruct the observations from the lake. You're trying to predict the reward from the lake. You're trying to predict the next latent from the current latent in action. And you just sum them up, and that gives you essentially your dreamer algorithm, right? And so the dreamer algorithm, at least this is what you do for model learning. And then once you have the model, you can like plan in the model to get action. The same way that we did this, right? But the difference is that we're not predicting model in states in observation space as much as we're predicting model in latent space, right? And so it just lifts up your prediction to latent space, and that like makes it work a lot better for images, for longer horizons and so on. So the dreamer set of methods has like a bunch of tricks on this base idea, and it works surprisingly. So yeah, that's the core idea. Just like lift up to latent space, predict in latent space, decode down to observations, and predict rewards. And so when you're planning, you can just like avoid coming down to observation space. You can just do planning completely in hallucination, right? And so you can say that like, at a particular observation, I've lifted into latent space, and then I know latent dynamics, right? I can like map into latent dynamics. I know latent reward. And so I can just like plan in this world for what action to take. Right? And so that tends to work pretty well. So you don't ever have to like, unlike these kinds of methods, which are generating videos, like you don't have to like rely on the generated videos for planning. Like a lot of these methods with generated videos, then try to like take actions that get this pixel to this pixel. And here you're not relying on that, you're just relying on your latent state space to keep planning. Okay, so that's basically it. How well does it work? It works pretty well on Minecraft. And so I think this is pretty impressive given how quick the camera is moving and like it being egocentric and obviously partially observed, right? Like you obviously can't see the whole world from your first person. I think it's pretty impressive how well this thing worked. Even though it looks like a dark screen, right? It's escaping. Good. And the thing that I found even more impressive was that they applied this to a bunch of robots. And so this is dog walking, some taking place. They have like a weird spherical robot that is rolling around, which is kind of cool. But all of these were like training in less than an hour from images in the real world, which is quite impressive. But yeah, that's just model-based RL from images. Like most of the methods that are successful, do something of this nature, unless Vishwas comes up with a new method, which we'll talk about in the next iteration. Yeah, that's kind of model-based RL. Any questions before I give some perspectives?
Theoretically, deviating from the Markov,
Yeah, it's not Markovian. Yeah, it's POMDP.
how does it work? Then like all the RL stuff they're doing for these models, it's still,
Oh, it's because your latent space is kind of like a belief state. And so if your latent space is a belief state, then you can like plan in belief state, and like you can show that any POMDP, if you like have the belief state, reduces to an MDP in belief state. And so their hope is that their like latent encoder is a belief state. Right? And so there's like there's some work. So this particular work tries to do it on like a sample ZT from the latent encoder. There's some work that operates on the whole distribution. And that is more like a belief state, and that's dense work. So think of it that way. There's still like difficult parts of like information gathering and these kinds of things in POMDPs, which these methods don't really solve. Or at least I haven't seen it. So yeah, that's still an open problem. Okay, so why should we care about model-based RL? One is that it transfers, right? So because you're just learning the dynamics independent of reward, you can swap out reward. It should give you a method to transfer. I'll talk about one of the papers we have been working on next class. Second is efficient. You can see Anusha's learning curve is like 1/100th of everything else. And so empirically, it's been found to be a lot more efficient, especially when operating from images and so on. It tends to do really efficient. And it's really simple in terms of like many things are just supervised learning, like learning the model or planning is just randomized shooting. And so to me, these feel like the big bonuses of this kind of thing, right? So transfer, efficiency, and simplicity. I think that was the most future-proof one. And so that's what a lot of our group is working on. Natural question to ask is, are these super different from Q functions, right? Q functions also model the future. But they model the future in terms of sums of rewards, and models model the future in terms of individual states, right? And so models and Q functions are kind of similar in that they're both off policy, they both model the future, and they're both quite different from policy grade methods, right? Policy grade methods are just trying to find what is the best action to take now, given that you're optimal. Whereas models and Q functions are saying, given a state and action, what is the future, right? So you can think of models and Q functions being causal and policies being anti-causal, right? And so that's how I think they're similar. Like models and Q functions go in the future and policies go in the past, right? So the policies say, I know I'm going to be optimal in the future. What would I do now, right? And this goes the other way. They're different because models do one-step modeling, while Q functions model the cumulative sum of rewards. The models model individual states, whereas Q functions model returns, right? So the benefit of doing that modeling state is you can swap out any reward, whereas Q functions work for a single reward, right? And so models, because they're just modeling states, you can evaluate arbitrary policies, you can do planning for anything. Whereas Q functions are tied to a particular policy pi, right? We talked about Q pi, evaluating Q pi. And so Q functions can't do every policy. And then a way I like to think about models is that they're like, take all your training data and they're like compressing your training data into your parameters, right? So it's like trying to say, I got a bunch of S, A, S prime. And a model can be thought of as just a compression of S, A, S prime into neural net parameters, so that if I feed an S and A, I will get S prime. And so you can think of this as parametric storage of your training data. And so it's like taking all your training data and compressing it. And Q functions keep around your replay buffer. So it's non-parametric storage. So it says you got S, A, S prime, just like keep it in a big buffer of data. And so this compresses that, and model and Q functions don't compress it. They're non-parametric. So yeah, that's how I think about the differences. They're both interesting. I think Q functions have less compounding error. Models have more generality, and I'll try to talk about some of our work that tries to bridge the gap. Okay, before we get into controllers inference, let's take like 3 minutes and we'll get back. Sorry, I couldn't see it. All right, guys, project's coming along. Ish. Anyways. I'm sorry. Well, good thing is I don't really care if it works or not. It's fine. It'll be fine. There will be an attempt. As long as there's an attempt and you enjoy the process and yeah, like when there's a certain momentum. Yeah, fair. But I do understand it's stressful. But
As for computation power, like how much more does model base you require compared to
model based. I guess that requires a different type of computation, right? Like model free will need like tons of GPU parallelization, and like lots of training time, right? So like the robot inference compute can be quite cheap because you're just deploying a policy.
Yeah.
Whereas in model based, you're often like running MPC or something on the fly at test time. And so the test time compute will be more intense, whereas the training time compute is cheaper because you just take supervised learning.
So, I mean, if we are using like reinforcement learning to model base.
Then yeah, both are similar,
Okay.
right? But if you're using these MPC type things, then hopefully. Okay. Cool. Let's keep going. I'm pretty excited about this next part. Control is inference is cool. But it's basically trying to use probabilistic inference as a tool to connect model-based, model-free, policy gradient, actor critic, all of these methods, and then hopefully also motivate inverse reinforcement learning. So the same framework is nice. And the great thing is Mo Todorov, who is faculty here, came up with a lot of these ideas. And so yeah, I think it's super cool. But yeah, let me try and motivate it a little bit, right? So so far we've been talking about like getting optimal policies. We've been saying optimal, right? And so optimal policies are trying to say, you're trying to do some objective like this. You're trying to say, let's maximize the expected sum of rewards with a policy, with a model, right? But it's like, you're trying to find the like a point estimate of what is optimal, right? And so we're assuming that, and we're trying to like model that as we're trying to model agents as rational, like completely rational, which means that we're saying that they're like reward maximizing agents, right? Now, why might that not be the right model? Why might it not be the right thing to maximize the reward could be wrong, right? Or you're trying to transfer to a new problem, and so you just like collapsing to a solution might not be right. Perhaps the most compelling one is if you're trying to explain behavior, right? So like, let's say you got human demonstrations and the process of inverse RL tries to say, take human demonstrations, infer reward. Like human behavior is rarely optimal, right? Like, and so I guess what that suggests is that like lots of real domains, right? So these are like some human motion capture, navigation in the city, muscular movement, right? A lot of these things are not really optimal. In the like reward maximization sense. They're like close to optimal and we talk about what that means, but like people tend to make mistakes, right? And if we use this hard notion of optimality, there's like things that are optimal and everything else is like not optimal, right? And so there's no like smooth notion of suboptimality. And so what we want is a soft model of optimality that doesn't just explain optimal behavior, but also explains suboptimal behavior. Right? And so like, but suboptimal behavior in like a structured way. And so what that means is like, things that are, certain mistakes matter more than others, right? So here's an example. You have a start, you're trying to get to a goal, right? When people are told to start here and go to this goal, they're not often going to take the shortest path, but most of the time they're going to get to the goal, right? So they'll try to do things that like kind of meander about and get to the goal, but they're like significantly more likely to do this than like some random thing off to the side, right? And so like there's a soft notion of optimality which says that things that are, higher reward are more likely, and things that are lower reward are less likely. And so rather than just saying things are like optimal or non-optimal, we want to build a notion of soft optimality, which says that like the likelihood of the behavior is proportional to its sum of rewards, right? Which says that things that are like the likelihood of a behavior is not just zero if it's not optimal, it's just proportional to how high its reward is. Right? So for instance, if you get huge negative reward for going this way, that's really less likely. But if the behavior ends up like kind of by the side here, it's like not that unlikely that you do it, right? And so a reasonable model of soft optimality could be trying to model behavior as proportional to the expected reward, right? So rather than relying on a purely deterministic notion of optimality, right? Like max or not max, you can try to go to a soft notion of optimality, which says that, some mistakes are more important than others, and you're going to model behavior as proportional to how good it is, right? And so it's not just going to be likelihood of 1 for optimal and 0 for suboptimal. It's going to be, likelihood higher for optimal behavior versus suboptimal behavior, where the likelihood depends on the return. Right? So it gives you a smooth notion of this is optimal, this is slightly less optimal, this is extremely less optimal. And these things, this will be the highest likelihood, this will be slightly lower likelihood, this will be very little likelihood, right? And so a notion of soft optimality goes from like a hard, like we started with a hard notion of max reward. And instead, we're going to try and come up with a probabilistic notion of optimality, which is going to say a behavior is proportional to how good the reward is. And so what that means is we want to have like, rather than the deterministic max reward, we're going to have a stochastic policy, which is generating behaviors proportional to the reward of these behaviors, right? So it's going to say, generate the highest reward behavior with the highest likelihood and the lowest reward behavior with the lowest likelihood, but it's not zero likelihood, right? So when we talked about optimality, it collapses to the policy generating things which are either optimal or like it's just going to generate optimal behavior and have zero likelihood of suboptimal things. Whereas when you talk about soft optimality, it'll have some likelihood of generating suboptimal behavior, but just proportional to the reward. Okay? And so it's going to say better reward trajectories are higher likelihood. You're going to go to stochastic policies. And this gives us like a probabilistic measure of optimality rather than just like a point estimate.
So like in this example, you have shortest path to so
That's right.
that's a high.
That's high.
Yeah, but what if you're doing something with another pretty common scenario where it's like reach a goal? So you want to reach the goal in shortest time? Like,
Can you repeat that last part?
what if it's like a reach avoid problem?
Oh, reach avoid.
They go through a bunch of obstacles, and so that's it's not very good. But going all the way around,
Yeah.
what you said would give you the low reward,
Right.
might actually avoid all this.
Right. So then in that problem, like in this problem, the reward is distance to goal. In that problem, the reward would include the void. Right. So
how do you include that?
like you would just like add it, you would like add a negative term to the reward, which is like avoid these obstacles. So you say like positive to reach the goal, negative to when you hit an obstacle. Right. So the reward is going to factor in that. Okay, so what we want to do is we want to move from this completely,
You said that like you're doing a point estimate.
Yeah.
But you never are, right? You're always some portion.
Oh yeah, so it's a good point. So you have to be careful about a point estimate of what, right? So we're saying we're doing a point estimate of parameters, right? But it's like a stochastic policy. Right? But the important thing is that in most problems, essentially all problems, the Gaussian collapses to a point estimate at convergence. Right, in the deterministic policy of convergence. Like most problems, you like end up with the deterministic policy because there always exists an optimal deterministic policy for a reward maximization objective. And so Yeah, where like you optimize this objective with the parameterized as a Gaussian, but the Gaussian collapses to something that's good question. Okay, so we want to move to a soft notion of optimality. And so we want to say, can we go from this problem of reward maximization, right, to a framework that affords like softer notions of optimality? And so it doesn't just collapse to zero likelihood on anything that's not optimal, right? And so we're going to try and use probabilistic inference as our tool, right? How many of you are familiar with probabilistic inference? Ish. Okay, so we're going to use probabilistic inference as our tool. And so we're going to say that here we were taking max with respect to sum of rewards, right? We're trying to find policies that maximize rewards. Instead, we're going to try and come up with a framework that says that policies will take actions proportional to their expected sum of rewards, right? So we're not going to say that policies are going to collapse to take actions which are 1 if it's along the max path and 0 otherwise. We're going to say policies are going to take actions which are proportional to the reward that they got, right? And you can change the proportionality, like you can change the temperature on it. But the point is that like things that have higher reward are more likely to be produced by the policy. Things that have lower reward are less likely to be produced by the policy. And so it's a soft notion of optimality. And you can think of this as like the policy is generating things proportional to exponential reward by some temperature, right? And if you drop the temperature to be really, 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 really small, then it becomes max, right? And so it's saying that like, if the temperature is pretty large, then you're gonna maintain likelihood over many different possibilities, right? Like the highest one is going to be the highest reward, next highest reward, next highest reward. But if you jack down the temperature, this is going to become like extremely peaky, which essentially becomes like a max, right? And so you can like smoothly interpolate from a soft optimality to a hard optimality by just changing the temperature. And we'll get to like what temperature means, etc. But just intuitively, you can think of this as like it's proportional to reward. You just change the proportionality term and it like jacks up the highest reward.
Was this also good for multi-variable
Yeah. That's yeah.
Does this have anything to do with like? This reminds me of when we had a data.
That's right. It's a derivation of the maximum entropy RL frame. Yeah, that's exactly right. Okay, so I think sampling and optimization have like lots of deep connections, right? So what we're trying to do is we're trying to say we're going to go from optimization to sampling or sampling to optimization. So for instance, like Langevin dynamics gives us a way to take like optimization and use it for sampling. And what we're going to do in control as inference is we're going to try and use sampling and probabilistic inference as a tool for soft optimization, right? And so for those of you who are familiar with diffusion models and Langevin dynamics of slope functions, that is going this way. So it's saying use optimization as a tool to enable sampling. And what we're going to do in control as inference is we're going to say, let's use probabilistic inference and sampling as a tool for optimization, for soft optimization, right? So these two fields are like super connected, and control as inference gives us a nice way to connect them in the context of reinforcement. Okay, so the main premise of what we're going to do is we're going to go from our maximizing reward framework to a framework of probabilistic inference for behavior. That's going to let us do like soft optimality, things like that, which are not just going to collapse to arguments, right? And so we're going to use probabilistic inference as our tool. Okay, everyone kind of with me? Okay, so if you want to do this, let's start with some background, right? So we're going to start with some background on probabilistic graphical models, right? And so a graphical model typically looks something like this. You have a bunch of nodes, random variables, right? And your nodes are connected by edges. And together, these nodes specify a joint probability distribution, right? So you have a A, B, C, D, E, your random variables, and you have a joint distribution over P of A, B, C, D, E, right? And what a probabilistic graphical model does is it finds a convenient way to encode a joint probability distribution with particular types of conditional independencies, right? And so it says that, like when you read this dynamics model, it's not just saying that this is an arbitrary joint. It's not saying that everything can depend on everything. It's not like a click. Instead, it's saying that, like, for instance, A doesn't depend on anything. C and B will depend on A. D will depend on C. D will depend on C and B, and E will depend on D, right? So it encodes a certain type of conditional independence, which is really simple to read. It just says that the joint likelihood in any probabilistic graphical model is a product of the likelihood of every random variable with respect to just its pairs, right? And so it's saying that like you can factor the joint, right? If I was just using chain rule to factor this, right? I would write this as P of A times P of B given A times P of C given B, A, etc. If I just like had no information about this joint, right? But this graph tells me more information. It tells me that the way I'm going to factor this joint is very specific. It tells me that the way I'm going to factor this joint is I'm going to write as P of A times P of B given A times P of C given A times P of B given B and C times P of E given D, right? So it's like take every node and it only depends on its pairs. And so you can think of like B is independent of A given C, right? And so it's like encoding conditional independences in your joint. And the easiest way to do it is just write it as a product of each node with respect to its parents. The likelihood of each node with respect to its parents. Right. And so that's the general framework of probabilistic graphical models. And each of these things you have like some conditional probability distribution that you specify, you learn, you know, depending on the setting, right? But all that a graphical model lets you do is take a joint and like express the conditional independencies in that joint. Right? Okay, so we've seen things like this before, right? Does anyone remember where we've seen this? Yeah, autoregressive models, or just like Markovian like dynamics, right? Whenever you just had Markovian dynamics, you had ST plus one, AT, right? And we said that when we decompose the trajectory likelihood, we already used this property. We said that the trajectory likelihood is the initial likelihood times P of S1 given S naught and A naught times pi of A naught given S naught. Like we already kind of used this property to decompose the trajectory likelihood, right? And so the point is that this graphical model, like this graphical model is for control, but it like encodes the like independency. So in that case, it encoded like the Markov property, right? And the Markov property is across time. In this case, it encodes certain dependencies between A and E, but it's like essentially just trying to like encode a probability distribution. Yes? Questions? We haven't like talked about how it's useful, but like this is just a basic framework. We've used this framework before to encode the Markov property. Okay, so what do we do with this kind of model? Like the nice thing about this model is that you can kind of read conditional independencies off this model, right? And so there's this nice technique called deseparation. And what deseparation says is that depending on whether something is observed or not, you can tell if two things are conditionally independent, right? So for instance, A and B, if you read this thing, A and B are not conditionally independent, but if A and B were given C as evidence, then they are conditionally independent, right? So I said, like imagine we had colored this node in, right? Like as in we had observed C. If you had observed C, then A and D are conditionally independent. So A is conditionally independent of D given C, right? And so if you have any graph like this, like these are just some rules that you could follow. Like the color, the dark one just says something is observed, and not dark is saying that something is not observed, right? And so whenever you want to like tell if two things are independent or not, you can try to like follow the path between them and try to see if the path is blocked or not. And if the path is blocked, then you know that they're not independent. Yeah, the path is blocked, you know that they are independent. And if the path is not blocked, then you know that they're dependent, right? And so, but the direction of the arrows matter. So if you like look at this direction of arrows, A and C are currently dependent, but given B, they're independent, right? And so let's ground it in an example we know. You have ST plus 1, ST plus 2, right? Markov chain. AT plus 2. We know that given, we know that given ST plus 1, ST and ST plus 2 are independent, right? And so you can think of the path between them as being blocked by evidence, and hence they're independent. But you have to be careful about the direction of arrows. And so we won't get too far into that, but it's like, it's an easy way to read conditional independencies off of your graph. Right? Okay, so the point of the probabilistic graphical model is it just lets you like establish conditional independencies. How does this connect to everything else? Well, what we're going to do is we're going to cast this problem of soft optimality as a probabilistic inference problem, right? And so what is probabilistic inference? It says that if I have a graphical model like this, right? And let's say I knew the conditional probabilities, I knew P of A, I knew P of B given A, I knew P of C given A, etc. Right? I knew all of these. What the graphical model lets you ask is like, what is the likelihood of B being a particular value given I know what C and D are? Right? And so it lets you ask queries about like conditional probabilities. So it says that like, what is the likelihood of B given evidence C and D? Or what is the likelihood of A comma B given the evidence C comma D, right? And so given some evidence of things that you've observed, like here's an example. It's like, given that you've seen that the ground is white, like what is the likelihood that it's green, right? And so it's like allowing you to ask queries about the likelihood of random variables given evidence, right? And so these are like your posterior inference queries because you're trying to establish this posterior, right? And so we're going to show a connection between policy learning, like things that are soft optimal, and probabilistic inference. Posterior, we're going to show that obtaining the optimal or soft optimal policy is the same thing as asking a posterior inference query, right? And so I think the thing that's cool is like this thing seems totally unrelated, right? It's like what the hell is this? Talking about rains and clouds and so on. And how do we connect this to like getting robots to do things? Well, we're going to show that for a particular choice of graphical model, which is our control as inference graphical model, you can show that finding the optimal policy is a posterior inference query. And you can use tools from posterior inference to do this, right? And so the way that people do posterior inference in like these kinds of models, when everything's like tabular, is they use these techniques called variable elimination, where you basically say you construct the joint, right? So you construct the joint and then you like eliminate out variables, right? So you can say that to answer this query, for instance, right? You can say this is like P of A, B, C, D, E. You sum out A, you sum out D, and then you like divide by sum D, sum A, sum B. You have A, B, C, D, E, right? And so you can use Bayes' rule to get there, but basically you can think of this as like take a joint, sum out D and A, right? So this gives you P of B, C, E, right? Just by like marginalizing out A and D. And you sum out DAB, and then you get P of C comma E. And so then you have P of BCE divided by P of CE. And so you get P of B given CE, right? So you can answer a posterior inference query by doing this type of variable elimination procedure. Right? So you can say that take the joint, sum out the variables that you don't care about, and then normalize to get the query that you want, right? So when it's a table, this is super easy. You just like do a bunch of matrix multiply. It's easy. When it's continuous, it's much harder, right? And we're going to show that we're like in control, we're going to do this continuous thing, and we're going to need all this approximation. But the point here is that posterior inference is just like asking, given some evidence, what is the likelihood of some random variable? In our case, we're going to say, what is the likelihood of the random variable we're going to ask about is the action. And we're going to say, like, given some state and some future outcomes that we care about, like, what is the likelihood of an action being taken? That's going to, we're going to show that's connected to optimality. So does that make sense as a premise, right? So the questions we want to ask is like, seems totally random. What does this have to do with RL? Isn't RL about maximizing expected reward? Like, what the hell does this have to do with maximizing expected reward, right? And so what we're going to show is that for a particular choice of graphical model, which is the control as inference graphical model, and a particular choice of posterior inference method, which we're going to use variational inference, we're going to show that RL is like policy grade, actor critic, model-based RL are all exactly approximations to that posterior inference point. Okay, we will get to it next time. I think it's going to be fun. But yeah, thanks.